Imagine throwing a ball at a wall. You'd expect it to bounce back, right? Now imagine the ball mysteriously appearing on the other side. Sounds like magic? In the quantum world, this seemingly impossible feat is a reality, thanks to a phenomenon known as quantum tunneling. Quantum tunneling is a bizarre yet fundamental concept in quantum mechanics, the theory governing the behavior of matter at the atomic and subatomic levels. It describes the peculiar ability of particles like electrons to pass through energy barriers, even when they don't have enough energy to do so, according to classical physics. Picture a tiny particle defying the odds and slipping through an impenetrable wall. That's essentially quantum tunneling. This mind-boggling phenomenon has profound implications for our understanding of the universe, from the way stars shine to the development of cutting-edge technologies. To grasp the essence of quantum tunneling, we need to abandon our classical intuitions about how the world works. In the quantum realm, particles don't behave like tiny billiard balls with well-defined positions and trajectories. Instead, they exhibit wave-like properties, described by a mathematical function called the wave function. Imagine for a moment that you're holding a rope tied to a wall. If you flick your wrist up and down, you create a wave that travels along the rope. Now imagine this rope encountering a narrow gap. The wave doesn't simply stop at the gap, instead a portion of it squeezes through and continues propagating on the other side. This is analogous to what happens in quantum tunneling. The wave function of a particle represents the probability of finding it at a particular location. When this wave function encounters an energy barrier, it doesn't abruptly drop to zero. Instead, it decays exponentially within the barrier. This means there's still a small but finite probability of finding the particle on the other side, as if it had tunneled through the barrier. Thinner barriers and higher particle energies increase the probability of tunneling. Quantum tunneling isn't just a theoretical concept confined to textbooks, it's a fundamental process driving various phenomena in our universe, from the heart of stars to the devices we use daily. One of the most striking examples is nuclear fusion, the process powering the sun. At the sun's core, immense pressure and temperature force hydrogen nuclei together, overcoming their electrostatic repulsion. However, classical physics suggests that the hydrogen nuclei don't possess enough energy to overcome this barrier and fuse. It's quantum tunneling that comes to the rescue, allowing these nuclei to tunnel through the energy barrier and fuse, releasing tremendous energy in the process. Another remarkable example is found in electronics. Transistors, the building blocks of modern computers and smartphones, rely on quantum tunneling for their operation. In transistors, electrons tunnel through thin, insulating layers controlling the flow of electrical current. Without quantum tunneling, our electronic devices as we know them wouldn't exist. The term quantum often sparks images of teleportation, the instantaneous transportation of objects from one location to another, as depicted in science fiction. While both quantum tunneling and quantum teleportation belong to the realm of quantum mechanics, they are distinct concepts with crucial differences. Quantum tunneling, as we've explored, involves the passage of a particle through an energy barrier, seemingly defying classical physics. It's a local phenomenon, meaning the particle doesn't vanish from one location and reappear at another instantaneously. Instead, it traverses the barrier, albeit with a probability determined by quantum mechanics. Quantum teleportation, on the other hand, deals with the transfer of quantum states, not the physical transportation of particles. It's a process where the quantum state of one particle, let's call it Alice, is instantaneously transferred to another particle, Bob, located at a distance. This doesn't mean that Alice physically travels to Bob's location. Instead, Bob takes on the quantum state of Alice, effectively becoming an identical copy. Can we tunnel through space? The idea of tunneling through space, much like a particle tunneling through an energy barrier, has captivated the imaginations of science fiction writers and enthusiasts alike. Could we one day bypass the vast cosmic distances by simply tunneling to our destination? While quantum tunneling is a real phenomenon, applying it to macroscopic objects like spacecraft faces significant hurdles. Firstly, the probability of tunneling decreases exponentially with the object's mass and the width of the barrier. For an object as massive as a spacecraft and a barrier as vast as interstellar space, the probability of tunneling becomes infinitesimally small, practically zero. Moreover, even if we could somehow overcome the probability barrier, there's no guarantee that the spacecraft would remain intact during the tunneling process. Therefore, while the concept of tunneling through space is intriguing, it remains firmly in the realm of science fiction for now. Quantum tunneling and faster-than-light travel, a distant dream. The allure of faster-than-light travel has captivated humanity for centuries, fueling countless science fiction stories and igniting our dreams of exploring the cosmos. Could quantum tunneling, with its ability to bypass classical barriers, hold the key to breaking the cosmic speed limit? Einstein's theory of special relativity, a cornerstone of modern physics, postulates that nothing can travel faster than the speed of light in a vacuum. This speed limit is not merely a technological hurdle but a fundamental limit imposed by the fabric of space-time itself. While quantum tunneling allows particles to penetrate energy barriers, it doesn't violate special relativity. The tunneling process itself is not instantaneous. It takes a finite amount of time for the particle's wave function to penetrate the barrier. Moreover, the information about the particle's presence on the other side of the barrier cannot be transmitted faster than light, ensuring that causality, the principle that cause precedes effect, is preserved. Therefore, while quantum tunneling offers a fascinating glimpse into the weirdness of the quantum world, it doesn't seem to provide a loophole for breaking the cosmic speed limit. Alien technologies and quantum tunneling. Food for thought. The vastness of the universe with its billions of galaxies and countless stars leaves ample room for speculation about the existence of extraterrestrial civilizations. If such civilizations exist, could they have harnessed the power of quantum tunneling to develop technologies far beyond our current understanding? The possibility of alien civilizations utilizing quantum tunneling for advanced applications is an intriguing thought experiment. Imagine, for instance, a civilization capable of manipulating quantum tunneling on a macroscopic scale, perhaps for transportation or communication. They could potentially tunnel spacecraft through interstellar distances, bypassing the limitations of conventional propulsion systems. Furthermore, they might have developed advanced communication systems based on quantum entanglement, enabling instantaneous communication across vast cosmic distances. However, it's essential to approach such speculations with a healthy dose of skepticism. Quantum tunneling's potential in space exploration, a glimpse into the future. While tunneling through space might remain a distant dream, quantum tunneling holds immense promise for revolutionizing space exploration in other ways. Its potential applications range from enhancing spacecraft propulsion systems to developing new materials with extraordinary properties. One area of active research is quantum vacuum thrusters, hypothetical engines that could propel spacecraft without the need for propellant. These engines are based on the idea of manipulating the quantum vacuum, a sea of virtual particles popping in and out of existence to generate thrust. Quantum tunneling plays a crucial role in these theoretical concepts, allowing for the manipulation of energy at the quantum level. Another promising avenue is the development of novel materials with enhanced properties through quantum tunneling. These advancements could significantly impact various aspects of space exploration, from power generation to data processing and communication. Conclusion: a universe of possibilities awaiting. Quantum tunneling, a phenomenon once confined to the theoretical realm of quantum mechanics, has emerged as a fundamental process shaping our universe and driving technological advancements. From the heart of stars to the devices we use daily, its influence is pervasive and profound. While the dream of tunneling through space or achieving faster-than-light travel might remain elusive, the potential of quantum tunneling to revolutionize space exploration is undeniable. As we continue to unravel the mysteries of the quantum world, we can expect to uncover even more awe-inspiring applications of this bizarre yet remarkable phenomenon. The future of space exploration is brimming with possibilities, and quantum tunneling is poised to play a pivotal role in shaping this exciting journey.